Good afternoon, class. We are looking at Chapter 3 Derivatives, Section 3.5, the chain rule. Here's the first part. We have covered the derivatives and rates of change, the derivatives as a function, basic differentiation formula, the product and quotient rules, and now the chain rule. We have seen the rise over run, the derivative at a specific point by taking a limit, and a definition which says dy dx is the limit of delta y over delta x as delta x approaches 0. Or f prime of x is the limit of f of x plus h minus f of x over h as h approaches 0. We also have seen many different formulas. The derivative of a constant is 0. The derivative of x to the power of n is n x to the power of n minus 1. The derivative of k times x is k. K is a constant. The derivative of e to the power of x is itself. The derivative of sine is cosine. The derivative of cosine is negative sine. Tangent gives us secant squared, cotangent negative cosecant squared x. Secant x is secant x tan x, cosecant x is minus cosecant x, cotangent x. Now we also added the product and a quotient rule with a quotient rules with a shorthand notation that the product rule is f prime g plus g prime f, and the quotient rule is f prime g minus g prime f over g squared. And now we are adding the chain rule, first reminding you of the composite function f of g means f of g of x. And if we want to differentiate that, we get f prime of g of x times g prime of x. Remember, f is the shell function, the outer function, the main function. G is the inner function. So we take the derivative of the outer function, and then we multiply by the derivative of the inner function. dy dx is dy du, du dx. This is in Leibniz's notation, where u is the intermediate variable. So to make some sense out of this, let's remind everybody of the composition function. So 3.5, the chain rule definition. The composed function f of g, the composition of f and g is defined as f of g equals f of g of x. If f of x is x cubed and g of x is 1 plus x squared, as a warm-up example, we want to look at f of g and g of f, reminding you of what we learned in algebra. So f of g of x by definition is f of g of x, which means f of 1 plus x squared. And if you plug it in here, we get 1 plus x squared to the third power. There is no need to raise this to the third power. In this case, g of f of x is g of f of x, which means g of x cubed, which means in this function, we replace the x with x cubed, and this must be raised to the appropriate power, giving us 1 plus x to the power of 6. And clearly, the two functions, f of g and g of f, are not equal. They become equal when the two functions are inverse of each other. As you recall, f of f inverse equals f inverse of f equals x. This is the only time, otherwise they are not equal, everybody. So how would you differentiate composite functions? Examples: y equals square root of 10x plus 5, f of x equals 10x squared minus 1. We use the chain rule. If g is differentiable at x and f is differentiable at g of x, then the composite function f of g of x is differentiable at x. So d dx of f of g of x is f prime of g of x times g prime of x. Or in Leibniz notation, y equals f of u. That means y is a function of u. U equals g of x. U is a function of x. Then dy dx is dy du times du dx. So the synopsis of that is, if capital F of x represents f of g of x, And we want to differentiate that. So d dx of f or g of x. F is the outer function, the shell, the main function. You're going to differentiate that. And of course, it's a function of g of x. So capital F prime of g of x. By the chain rule, because this is not x, we need its derivative times g prime of x. As an example, when we look at the basic power rule, d dx of x to the power of n is n x to the power of n minus 1. Now we want to go with the general or extended power rule, where instead of x, we have a function of x, such as g of x, h of x, f of x. When we want to do that, according to this, we need the same n sits in front. We need x to the power of n minus 1. Now we have g of x to the power of n minus 1. And then g prime of x. Think about it this way. If you are raising x to the power of n, you need the derivative of x, but the derivative of x is 1. But in this case, you need the derivative of g, and it's not 1, so you need times g prime of x. So in a matter of comparison to the basic power. A set of examples that will help us understand this concept would be a bunch of sinusoidal functions. Sine 2x, sine x squared, sine squared of x. We want to distinguish among those. And if you want to differentiate any sinusoidal function, I highly recommend you do the following. You read and pause. So I'm going to read this as a sine, and I'm going to pause. I know that the derivative of sine is cosine. We need to have an argument, otherwise sinusoidal functions make no sense, any trigonometric function. Therefore, sine needs an argument. It's called argument of a sine. And its argument is 2x. So does its derivative. So the argument is 2x. If it were x, we would be done, but it's not. By the chain rule, we need the derivative of that. We put it in front, and we are done. So y prime is 2 cosine of 2x. We do the same thing here. We read y equals sine, and we pause. The answer is again cosine. Every trigonometric function must have an argument. The argument of sine is x squared. So cosine of the same thing, x squared. By the chain rule, you need the derivative of x squared, which is 2x. You put the 2x in front. Y prime is 2x cosine x squared. The last one, if it helps, you can rewrite it as sine x to the second power. And now we use the extended power rule, and we write y prime is n, which is 2, g of x, which is sine x, to the power of n, which is 2, minus 1, times the derivative of g of x, which is sine x, and its derivative becomes cosine x. So we have 2 sine x, cosine x. This should help us understand the chain rule better. Now I want to look at two methods for differentiating the first example. Y is u to the power of 5, which makes it a function of u. U is 10x cubed plus 2, or g of x, which makes it a function of x. And according to the Leibniz's notation, dy dx is dy du dx. Notice these two are the same. If we treat them as fractions, and we can't, they cancel each other. So it works out this way. So what is dy du? You got to differentiate this with respect to u. So u is the independent variable, and it makes it 5u to the power of 4. du dx, simply differentiate this with respect to x, which makes it 30x squared. And at the end of the story, as far as the calculus is concerned, we are going to replace the u with 10x cubed plus 2. So we're going to have 5 times 10x cubed plus 2 to the power of 4 times 30x squared, putting these two together, and in the front, we get 150x squared times 10x cubed plus 2 to the power of. This is simple enough that we can easily find their composite function, f of g or f of g of x. So f of g of x means replace the u with 10x cubed plus 2 and raise it to the power of 5. And to differentiate this, we are going to go to the extended power rule. If it helps, you can even call this g and do the math. So n is a 5. So we are going to use f prime of x, f prime of g of x times g prime of x. So 5, so to differentiate this, 5 sits in front, the same thing to the power of 4, because n minus 1 results in 5 minus 1 being 4. Now, by the chain rule, this means the derivative of the inside, which means 30x squared, or you can look at this one. This is your g of x. Okay, so this is your g of x, everybody. G prime of x, 30x squared. Again, put it in front, and you get the same answer as before, 150x squared times 10x cubed plus 2. We are going to look at more examples. We want to differentiate this. We are going to follow that, and if need be, you can even write this as either g or even g of x. So with that being the case, 50 sits in front. G of x to the power of n minus 1, so the parenthesis to the power of 50 minus 1 of 49 times g prime of x, the derivative of the inside, which is simply 20x. Done with calculus, the product of these two is 1000x. We bring it to the front. Y equals square root of 10x plus 5. To differentiate and use the power rule, or in this case, extended power rule, we rewrite it as 10x plus 5 to the power of 1/2. Then we use this one again. If you want to write, this is the g function or g of x, that's fine. Again, if I'm differentiating, I'm going to write the formula from the memory, and I'm going to follow that. So according to this, I need n, or 1/2, the exponent, and then g to the power of n, so 10x plus 5 to the power of 1/2 minus 1. 1/2 minus 1 results in negative 1/2. So 1/2 minus 1. And then the derivative of the inside, according to the chain rule, and that makes it 10. The product of 10 and 1/2 is a 5. So we can write 5 and take 10x plus 5 to the denominator and change the exponent to positive 1/2. And of course, we are going to put it in the same format we received, okay? 5 times 3x minus 2 quantity to the power of 4. This is your g function. So the 5 remains, everybody, first. Now we just work with this one. 3x minus 2 to the power of 4. We follow the extended power rule. So we bring the 4 in front. Same thing to the power of 3. And then 3x minus 3 is 3. The product of 5 and 4, 20 times 3 is 60. We bring it to the front. 60 times 3x minus 2 to the power of 3. So we are using the extended power rule. basically in all of these cases. Now, we remember the derivative of e to the power of x is e to the power of x, and the derivative of f of g of x is f prime of g of x times g prime of x. And we want to differentiate y equals e to the power of 10x. So in this case, the exponent was x. In this case, is no longer x, but rather a function of x. You can think of it as g of x. So the derivative of e to the power of g of x, therefore, is itself times g prime of x. This is by the chain rule. Therefore, if you have e to the power of kx is e to the power of kx times k. And we put it in front. So if I'm differentiating this, because I'm dealing with the exponential and the base is e, I start just writing whatever I have. Repeat the function, e to the power of 10x. Then I look at the exponent. If it's x, I'm done. Because it's not, and I'm going to call it g of x, I need g prime, which is 10. I put it in front. I'm done. Y equals e to the power of t squared. Again, I notice I have an exponential function. I just repeat the question, the function. So if you think of this as the g function, then you need g prime by the chain rule. That means 2t. I put it in front. I'm done. I want to differentiate this. It is better to rewrite it first as e to the power of 2t. I'm using the rule of exponents for the power rule, t times 2. So e to the power of 2t, which is algebraic step. Then I'm going to differentiate. Because the exponent, the base is e, the answer is itself. And if you call this one g, I need g prime, which is 2. I put it in front, and I'm done. So that's dealing with the exponential. So in short, you are differentiating an exponential function. You just write the function and then times g prime of x. That's it, which is the derivative of the exponent. Of course, we're talking about base being e. We are going to differentiate y equals 5x times 3x minus 2 to the power of 4. And I'm going to show you a couple of different ways, but quickly, this is easy to see that it's the product of 5x and 3x minus 2 to the power of 4. That means we are going to use the product rule. So I'm going to call it, this is the f function. This is the g function. We need to use the product rule. So this is f. The derivative of 5x is 5. That's f prime. Then g, just write 3x minus 2 to the power of 4. Plus g prime f. Now I need the derivative of this, which I'm going to use the extended power rule. First, I'm going to need 4. Then I need the same parentheses to the power of n minus 1. 4 minus 1 makes it 3. And then I need the derivative of the inside, which gives me 3. So this is completely differentiated. Now go back to the product rule. G prime is this thing times f, 5x. And I'm going to write f prime g plus g prime f. So I hope you see that. This is f prime. This is g. That's easy to see. This whole thing is g prime. And of course, the first function f is 5x. Now, the algebra begins. Everything is done as far as calculus. So there is only one step of calculus. Class, here's the only calculus step you're done. So in order to finish that, we are going to factor. To do the factoring, so I'm going to put 4 and 3, 12 times 5x together, put it as 60x in front, and I'm going to factor the common factor between these two expressions. Between 5 and 65 is in common. 3x minus 2 is in common. One has exponent 4, one has exponent 3. We're going to take the exponent 3. So 5 times 3x minus 2 quantity cubed. But what comes out of this one and this one, we are going to discuss that in a moment. And so this, you divide by this. You get one factor of this, 3x minus 2. This, you divide by this. This completely goes away. 60x divided by 5 gives you 12x. This is fine. This is fine. The brackets, we combine the 3x and 12x into 15x. We get 5 times 3x minus 2 cubed, as we have it here, times the brackets changes to 15x minus 2. We are done. Now, what I want to mention is this. If this number 5 is involved, meaning it's either very large, like 5,000, or it's a fraction, 2/3, or it's 5.189, you really don't want to think of this as f of x. Rather, you want to do this with a bracket here and think of this one as the f, this one as the g, and this is a common factor that remains throughout. So look at what happens, class. If you look at this one, we kept the 5 out. So instead of 5x, you're dealing with x, the derivative of that is 1. Do you see that? 3x minus 2 to the power of 4 remains the same. Now this remains the same. Instead of 5x, you multiply by x. And notice this 5 carries out. So it remains, it doesn't go away. So the point being, if this number gets involved, you don't want to involve it with the differentiation. Just put it outside with some brackets and deal with the inside. If the fraction contains a numerator which is a number only, you don't have to use the quotient rule. You rewrite it as such, 7x squared minus x to the power of -4, and use the extended power. So if this is your g function, and you can even write it if you will, you can write this is the g or g of x. So according to the extent, so I'm going to write that according to the extended power rule, I need the n, which is -4. Then I write the same thing, 7x squared minus x to the power of, subtract 1 from here, you get -5. So this is -4 minus 1, -4 minus 1. Then I need g prime The derivative of the inside is 14x minus 1. And of course, this goes down. Remember the negative exponential rules. I have them all here, okay? So negative goes down, becomes positive, or comes up, becomes positive. So this goes down, and this -5 changes to a positive exponent. Minus 4 times 14x minus 1 over 7x squared minus x to the power of 5, and you're done. However, if you're dealing with a case like this, you should not avoid dealing with the quotient rule. So we are going to use the quotient rule. F prime g minus g prime f over g squared. So f prime is 1 times g, just write the denominator next to it, minus g prime. To take the derivative of this one, we are going to go with the extended power rule. We put the 4 first. Then we put the same parentheses, and the exponent is 4 minus 1 or 3. And then we need the derivative of the inside, which is 2. And then we go back to the quotient rule. This is g prime f. We need x. And again, with the quotient rule, g squared. So you want to square that. So the 4 changes to 8. The exponent 4 doubles up. We're done with calculus. We are going to simplify this. And to do so, we notice that they have 2x minus 1 in common. One has exponent 4, one has exponent 3. So 2x minus 1 cubed is the common factor of these two pieces. So when we divide this one by this one, gives us 2x minus 1. When we divide this one by this one, gives us minus 4 times 2 times x minus 8x. So again, minus 4, 2, and x, their product is minus 8x. This as an exponent 3 completely goes away, and the exponent over here becomes 5. So this would be the denominator, 2x minus 1 to the power of 5. The numerator would be 2x and minus 8x combined into negative 6x minus 1. All right, so y equals 4 over the square root of x squared plus 3. Square root of x is x to the power of 1/2. So this is x squared plus 3 to the power of 1/2 comes up and becomes negative. So 4 times x squared plus 3 to the power of negative 1/2. Now we want to differentiate this using the extended power rule. So this is 4, a multiplier, a coefficient remains. This is your g function. And again, by the way, as mentioned, because it's a fraction, but the numerator is just, you don't have to use the quotient rule. So negative 1/2 according to this, and negative 1/2 sits in front. Then you write g of x, the same thing, x squared plus 3 to the power of n minus 1. So minus 1/2 minus 1, you subtract 1 and it makes it minus 3/2. And finally, you need g prime of x. The derivative of the inside is 2x. And you're done with calculus again. Now the product of 4 and negative 1/2 is negative 2 times 2x makes it negative 4x. This is minus 4x over x squared plus 3 to the power of 3/2. And we rewrite it in the same format that we found it here. That's why I'm going to change that. But if you don't change it, it's not that big of a deal. But it's better to change it to the following format. And y prime, therefore, is minus 4x over the square root of x squared plus 3 to the power of 3. You want to differentiate this, and I remind you that when we do the sinusoidal function, the way I do it, I'm going to read cosine and I'm going to pause. I can't emphasize this enough. For me, it works out. The moment I see a sinusoidal function, I say cosine, I stop. I know the derivative of cosine is negative sine, so I'm going to write negative sine. Every sinusoidal function requires an argument. This is the argument, so this requires the same argument by the chain rule times the derivative of this piece, which is 12t cubed. I even put this formula for you, d dx of cosine of g of x. First, the cosine x is minus sine x. If it's cosine of g of x, is minus sine of g of x. And then by the chain rule times g prime of x. This is by the chain rule. Needless to say, you bring it to the front and you make it minus 12t cubed sine of 3t to the power of 4.